In this video, we are going to look at a type of first-order differential equation that's neither separable nor linear. So that means we can't use our separation of variables technique, and we can't use our integrating factor technique. Right? But what we're going to be able to do is to make a fairly standard substitution, and we'll be able to transform that differential equation into one that is separable, right? And let's just talk a little bit about substitutions. You've seen substitutions in your work in calculus before. So you've used u subs for antiderivatives. You've used trig subs for antiderivatives. And the whole goal of a substitution in a problem like that is to convert the problem into one that is easier but equivalent to. So you can solve the easier one and then somehow revert back to the original problem, right? It's the same idea that we're going to take, but now we're going to apply it to differential equations, right? So what do these look like? Well, on one hand, they're general, but then they all have something in common. So a dE, right, of the form, and here is its form. So it's the normal form, so we'll have the dy dx isolated. And there's going to be some function on this side that has x's and y's, right? And we've seen that form before, but now it's going to look something like this. You're going to have f, and then sort of as that inner function, you're going to see an expression ax plus by plus c, where a, b, and c are constants, right? And some of them might be 0, but they can't all be 0, put it that way, all right? And a dE of this form, right, may be transformed into a separable dE by using the substitution. Right, what does this substitution look like? So by using the substitution, u equals ax plus by plus c. Right? So essentially, we're going to utilize this inner function here, this ax plus by plus c, and our goal, right? So the goal is to transform this differential equation where we have a dependent variable of y and an independent variable of x. We want to transform it into one where the dependent variable is now u, and we want to keep x as our independent variable. So the goal is to produce a separable dE with dependent variable u and independent variable x. So it's like we're changing over from a y unknown to a u unknown, but in the u form we will be able to apply our the separations of variables methods, right? Okay, so what is it? Oh, that looks like an A, or that looks like an E, right? Okay, so how does it work? Well, it's best to see it in action, right? So let's start. We'll do a couple examples. So let's say here's my dE, and it's written in the normal form. So dy dx is equal to, let's say it's secant of x plus y minus 1. And let's make it an initial value problem. Let's say that y of 0 is equal to, let's say, pi over 2. All right? So this is our initial value problem. And this one, we can see that it's not separable because in here what I have is a sum of x plus y inside my secant function. And there's no way for me to factor this. Not only that, but here, look, we have this extra minus 1 here, right? So there's no way for me to factor this into a product that involves only x and then another factor that involves only y. I can't do it. And it's definitely not linear because look at what we're doing. We're taking the secant of x plus y. We're not allowed to take, the secant of our dependent variable, right? So this differential equation is neither separable nor linear, right? Let me just make a note here. So this dE is neither separable nor linear. But what I have observed is that here's that inner function, this x plus y. So I'm going to take this substitution, right, and I'm going to let my u be the inner function. Very similar to what you do when you're using a substitution to evaluate certain integrals, right? So we're going to let u be equal to x plus y. Now, think back to when you do a substitution. The next step is to take the derivative, right? You need to figure out your du. Well, actually, what we want to do, we're going to take the derivative of both sides with respect to x, right? So after you've chosen your u, we differentiate. So we're going to differentiate u with respect to x, and then that will give me 1 plus. Now remember, y is dependent on x. So when I differentiate it with respect to x, I will get dy dx, right? So this here gives me the relationship between x, y, and u. This equation gives me the relationship between du dx and dy dx. And in fact, what I can do, I can solve this equation for dy dx. So dy dx is equal to du dx minus 1. So this that I've boxed off in green is going to become u, and this that I have in blue is going to be my dy dx. And that's how I can convert this differential equation where my dependent variable is y. I can now convert it into one where my dependent variable is u, right? And hopefully it's one that we can solve by separation of variables. So let's see what it looks like when I convert it over. So instead of writing dy dx, I'm going to write du dx minus 1. So du dx minus 1 is equal to, and instead of writing the secant of x plus y, I'm just going to write the secant of u. And then I still have my minus 1 on this side. But the nice thing is now the negative 1's cancel out, right? They cancel out completely. So if I add 1 to both sides, it goes away. And then here is the normal form for my new differential equation. Right? So here's my new differential equation, and it is separable because I can take over the dx and I can divide through by the secant of u. So this one now, right, is separable. And the whole idea of this process is that once your differential equation is of that form where you can identify an inner function where it's essentially a linear function in terms of x and y, this type of substitution will always make it separable, right? Now, it doesn't always mean that the algebra and the calculus will be easy. That depends on the function, but we will always be able to separate the variables. So let's multiply both sides by dx and divide both sides by the secant of u. And it looks like this, right? And now let's integrate both sides. Now, to integrate 1 over secant is cosine. So let's rewrite that in a simpler form. So on this side we have the cosine of u du, that antiderivative, and on this side doesn't get any easier, we're just integrating dx. So when I integrate my cosine function, I will get my sine function, so this is the sine of u, and then on this side I'll have x and then plus c. Okay? So this is the general implicit solution for u. But my goal was to solve for my original y. So remember what we said was our u equation? It's x plus y. So what I'm now going to do is revert back and replace this u with x plus y. Right, so I have this, so then the sine of x plus y is equal to x plus c. At this point, let's go ahead and use our initial condition. Our initial condition, just to remind you, I believe it was when x is 0, right? When x is equal to 0, y is equal to pi over 2. Okay? So let's utilize that. So when x is equal to 0, y is equal to pi over 2, so I have this equation. I have the sine of 0 plus pi over 2 is equal to 0 plus c. So I have the sine of pi over 2 is equal to c. Well, the sine of pi over 2 is 1. So my constant is 1. Right, so now I have my particular solution, right, because I figured out what my constant is, and now the question is, can we isolate the dependent variable y? Can we get it in that explicit form? That's like our gold standard. Well, yes we can, because we can use arc sine, so we can take the arc sine of both sides, and it looks like this. Now, if you're used to writing arc sine, you can write it as literally arc sine of x plus 1, right? In fact, this is the form that a lot of computer algebra systems recognize. Things like MATLAB, Maple, Mobius, they all use some version of this arc notation. They don't use the -1 for the inverse sine function, right? And then once we have it in this form, then we can subtract x from both sides and get our explicit particular solution for y as a function of x. So we end up having arc sine of x plus 1 minus x, right? So that's our solution, right? So again, it's a fairly straightforward process. The only curveball that can pop up every now and again is maybe you have to use I don't know, a partial fraction for your integral or integration by parts. You just don't know. It depends on how the function is set up. Right. Let's do a second example so we can see what this process looks like. And let's see. So second example. So example 2. And let's see, we're going to solve. So here is so dy dx is equal to negative 2x plus y squared. And then on this side, let's make it like plus 11. And then we have that y of 0 is 0, right? So we have another initial value problem. Again, this is something that is definitely not separable because of this. We have, again, a sum of x plus y, and then it's being squared, so it's definitely not linear. And the question is, how do we go about solving this? Well, what we do recognize is this inner function here again, right? This negative 2x plus y. So we're going to let that be our u, go through our process, and see what if we can convert this into one that is separable. So let u equals negative 2x plus y. And just like any other substitution problem, once you've identified your u, you then differentiate it. And we're going to differentiate with respect to x. So du dx, this gives me negative 2. And then this y, when I differentiate it, becomes dy dx. Right? So let me solve this for dy dx. So we're going to have dy dx is equal to du dx plus 2. Right? So what I have there in green is going to become u, and what I have here in blue is going to replace my dy dx. Right? So let's write down the new differential equation with the dependent variable of u. So we're going to have du dx plus 2 is equal to, and then all of this is just now u squared, and then I have a plus 11 here. And then, right, so there we go. So now, unlike the first case where the constants completely canceled out, they're not going to cancel out completely. What I'm going to have left, if I subtract 2 from both sides, I'll have that du dx is equal to u squared plus 9. Right? Now this is separable, right? So first, if I multiply both sides by dx, I will get the quantity u squared plus 9 times dx. But then if I divide both sides by the quantity u squared plus 9, I will have it in that separated differential form. So I have 1 over u squared plus 9 du, and then that's equal to dx. So now I can integrate both sides, right? And hopefully, let's see if we'll be able to isolate our u. Well, how do we integrate u squared plus 9 du? Well, it might be a while since you've used it, but this is a result that involves arctangent, right? And let me remind you of the general result. And I'll write the result in terms of x, but if you integrate 1 over x squared plus a squared dx, that becomes 1 over a times the arctangent of x over a plus c. So in this case, my a squared is 9. So then my a squared is 9, so a is equal to 3. So from this, let me write it down here. So a squared is 9. and therefore A is equal to 3. So this becomes 1/3 arctangent of u over 3, and then on this side we'll have our x and then our plus c, right? And let's go ahead and we can go ahead and reverse the substitution. Now remember, we had let our u be negative 2x plus y. So I'm going to put that in here. So this implies that 1/3 arctangent of negative 2x plus y over 3 is equal to x plus c. All right. First, what I'm going to do is go ahead and try to solve for c. And let's use our initial condition. This initial condition, let me remind you, I think it was y of 0 is equal to 0, right? Yep, so right there. So y of 0 is equal to 0. So when x is equal to 0, y is equal to 0. Let's plug that in. So when x is equal to 0, y is equal to 0. So we have 1/3 arctangent of 0 over 3, so that's just 0, and then that's equal to x, well, x is 0. So, so 0, and then plus c. But the arctangent of 0 is 0, so that my constant comes out to be 0. Right? So that's handy. That should make it a little bit easier to solve for y. Hopefully we can do that. So here is our implicit particular solution. It's implicit because we have not yet solved for y. Right? So let's carefully go through trying to solve for y. So multiply both sides by 3. So that gives us arctangent of the quantity negative 2x plus y over 3. That's equal to 3x. Then take the tangent of both sides to get rid of arctangent. So when we do that, we're going to be left with the quantity that's in the parentheses. So negative 2x plus y over 3 is the tangent of 3x. Then multiply by 3 again. So negative 2x plus y is 3 tangent of 3x. And then finally add 2x to both sides. So we end up with y is equal to 2x plus 3 times the tangent of 3x. And that is our explicit particular solution, right? So these solutions by substitutions, it's again very straightforward, but as you can see, when you get to the part of evaluating your antiderivatives, any of our techniques from before could pop up. So it's always a good idea to brush up on your antiderivative skills, have your basic rules for derivatives and antiderivatives handy. That's helpful. And then obviously algebra plays a big role as well. All right, let's see you in the next video.